In this section of Module 2, we continue with the concept of peripheral IC interfacing with the 8085 microprocessor, looking at the programmable interval timer as the peripheral IC to study. The 8253 is the programmable interval timer IC. The 8254 is the latest and upgraded version of the 8253, and it is pin compatible. A programmable interval timer is used to generate accurate time delays, which can be used for applications like a real-time clock, event counters, and a square wave generator, etc. This chip has got 3 counters, which are 16-bit each. The slide shows the general counter and time delay flowcharts. A counter is used to keep track of the number of events. A time delay is used for setting up the timing between 2 events. The flowchart on the left shows the programming for a counter. Initially, the value is written into a register. You display the value and then you update the value by incrementing the register, and you check, is this the final value that you want? If not, you loop back and repeat the process. Again the value is displayed and again it's updated when the next event happens, and then you check, is it the final value? Once the final value has been reached, the counter will exit the loop. The delay is shown on the right hand side. In this case, you load a register with a value for the delay that depends on the number of clocks that's counted, and you decrement the register value and you check, has it become 0? If not, you go back and repeat the process. So you go back and then you decrement the value again it's checked, and then you loop back, and once the value has reached 0, we will exit from the delay loop. This is the pin diagram for the 8253. Similar to all the other peripheral ICs, on the left hand side we can see the data bus bits D0 to D7, which connects to the microprocessor data bus. Then we have 3 counters. Each counter has 2 inputs. There is a clock input and a gate input and an output from the counter. So that's clock 0 and out 0 and gate 0 on the left hand side, and on the right hand side we have clock 1, gate 1 and out 1, and also clock 2, gate 2 and out 2. And since there are 3 counters and there will maybe a control word which you want to address, we have 2 address bits. The address bits are A0 and A1. Depending on the address bits, the value from D0 to D7 gets written into the appropriate register. Then we have a chip select as usual, and a read bar and a write bar, which are the read and write enables, a VCC, which is the power supply, and the ground. Here we have the description of all the pins. D0 to D7 is the data bus, 8 bits. Clock, gate and out, N is the number of the counter. So clock N, gate N, out N stand for the counter clock inputs, counter gate inputs and counter outputs. Read bar and write bar are the read counter and write counter data enables. CS is the chip select, A0 to A1 is the counter select. You can have 3 counters and maybe the control word. VCC is plus 5 volts and GND is ground. This is the internal block diagram of the 8254, and we see the internal data bus of 8 bits with the 3 counters arranged on the right hand side with the counter outputs, clock 0, gate 0, out 0 for counter 0, clock 1, gate 1, out 1 for counter 1, clock 2, gate 2, out 2 for counter 2. And then on the left hand side we have the interface towards the microprocessor, and so does the data bus buffer which is connected to the bidirectional bus, which can connect to the microprocessor. And then the read-write control logic signals and the address goes to the read-write logic with a chip select. So there is read bar and write bar, which are the read and write enables, A0, A1 for addressing the various counters and block and the control word. And the control word register is also shown on the left hand side, and that's the address for the control word register is A0 and A1 are both ones. A0, A1, 00 addresses count 0, A0, A1 equal to 0, 1 addresses counter 1, A0, A1 equals 1, 0 addresses counter 2. This shows the control word for the 8253 programmable timer IC. The control word is 8 bits with D0 to D7. There are 6 different modes for the counter operation. The modes will be described later, but using 3 bits we can select one out of the 6 modes. So the mode bits are D1, D2, D3, which form the mode bits M0, M1, M2, and the way it is encoded is shown. Then we need 2 bits to select one out of the 3 counters. So bits D6 and D7 are the select counter bits, SC0 and SC1. So 00 selects counter 0, 01 selects counter 1, and 10 selects counter 2. Then we have 2 bits D4 and D5, which are the read-write control bits, RW1 and RW0. So when RW1 and RW0 are both zeros, the counter is read as a latch. The counter output is latched without stopping the counter, and it continues to run. So you latch the entire 16 bits onto 2 registers and you can read that. If the read-write controls are 0, 1, then we are going to read or write only the least significant byte. So only the LSB 8 bits will be read out of the total 16. If it is 1, 0, we will read or write only the most significant byte. If it is 1, 1, we will do it in 2 steps. We will read or write the least significant byte first, followed by the most significant byte. There is one more bit, that's bit 0, which can put the counter in a BCD counter mode, that's binary coded decimal. So bit 0 is 0 means it's just a binary counter of 16 bits. If bit 0 is 1, then the counter is arranged as a binary coded decimal or BCD counter with 4 fields or decades. This picture shows the 6 different modes of the 8253. Mode 0 is in the interrupt on terminal count mode. So when the count is over, it will send an interrupt to the microprocessor. Mode 1 is a programmable monoshot. Mode 2 is a rate generator. Mode 3 is a square wave generator. Mode 4 is a software triggered strobe. And mode 5 is a hardware triggered strobe. This slide shows the output waveforms for all the 6 different modes in one picture. So we have the output for the mode 0, which is the interrupt on terminal count, mode 1 the programmable one shot, mode 2 the rate generator, mode 3 the square wave generator, mode 4 the software triggered strobe, and mode 5 the hardware triggered strobe. Each of these cases are explained individually in the following slides. This shows the mode 0 operation or interrupt on terminal count. The value n, which is equal to 4, is written into the counter. The output or the interrupt signal is low in the beginning. After the clock runs, from the point where the value 4 is written, it counts down on each clock 4, 3, 2, 1, 0. When the count reaches 0, the output goes high, and that is used as an interrupt signal. The second half of the picture shows the operation of the gate signal for the count. Here we write the value m, which is equal to 5, into the counter. So at that point, the register has the value 5. The gate is high, so we start counting, decrementing the count. So it goes from 5 to 4. After that point, the gate is pulled down to 0. So the decrementing stops until gate is pulled up again. So those 3 clocks in between, the count does not decrement. And once gate goes high, the count continues to decrement from 3 to 2 to 1 to 0 on each clock. When the count reduces to 0, the output goes high, and that is used as the interrupt for the microprocessor unit. Mode 1 is the programmable one-shot. In this case, the output is high in the beginning. At that point, we write the value n into the counter. N is equal to 4. So when we raise the trigger, the output falls to 0, and then the count starts decrementing from 4 to 3, 2, 1, 0, decrements on every clock. When the value reaches 0, the output rises, generating the one-shot pulse. We could also stretch the counting by pulling down the trigger in the middle of the decrementing sequence. So that's shown at the bottom. In the beginning, the output goes low when the trigger goes high, and then you start decrementing the count. In between, the trigger is pulled low. At that time, the count does not decrement. Then it starts decrementing again when the trigger is pulled high. So finally, when the decrementing count reduces to 0, we get the one-shot pulse. Mode 2 is called the rate generator clock mode. So just look at the first 3 signals. We have a clock, and then we write the value n equal to 4, which creates an output pulse when the count reduces to 1. So we don't have to wait until count reduces to 0. When the count reduces to 1, it creates a pulse, low pulse for 1 clock cycle. So again, we load n equal to 3, and from 3 it counts down from 3 to 2 to 1, and when it reaches 1, it creates a low pulse for 1 cycle, and that repeats 3 2 1, again a low pulse. So that's what is shown in the upper half. In the second case, we write n equal to 3, and in between we pull reset low, so the value gets changed back to 3 again, and from 3 to 1 we get a low pulse, and again 3 2 1 we get a low pulse, and it repeats. Mode 3 is a square wave generator. In this mode, if we write the count value equal to 4 or an even value, every clock the count is reduced by 2. In the beginning, the output starts off as high, and after 2 clocks the output reduces to 0, and this repeats continuously. So again, after 2 more clocks, the value of the count becomes 4, and you get the output high. 2 clocks later, the value of the count is reduced, and then it gets a low output, and we get a continuous square wave. Suppose the value written in the counter is an odd number, then the pulse stays high for n plus 1 by 2 clock cycles and stays low for n minus 1 by 2 clock cycles. So that is what the asymmetrical square wave that is shown just below the square wave for output equal to 4. The frequency of the square wave is equal to the frequency of the clock divided by the count. In mode 4, the counter is used to produce a strobe-like output. So in the beginning, the output is high. We write the value for the count in the register n equal to 4. From that point onwards, the count starts decrementing, and after the value 4 reduces to 0, it sends a pulse for one cycle, after which the output becomes high again. We could also control the timing by using a gate signal, at which point the decrement stops. So in the beginning we load n equal to 4 as before. The output will be high, and then after one clock the gate signal for the counter is pulled low. So we start to count again from 4 when the gate signal is pulled high. So again we go from 4, 3, 2, 1, 0, and we get a low pulse for one cycle when the count reduces to 0. Mode 5 is the hardware triggered strobe, which behaves similar to the software triggered strobe, except in this case we use a hardware signal, which is the gate, to control the counting. So in this case also, the output is high in the beginning and the value 4 has been written in the counter, and the counting does not start until gate goes high. So gate is the hardware trigger. When gate goes high, the countdown happens. We count down from 4 to 3 to 2 to 1 to 0. When we hit 0, the output falls for one cycle, creating a pulse. We could again control the timing by pulling gate high and low once the count begins. So the second uh, part, we see the output is high in the beginning. The value n equal to 4 has been written in the counter. When the gate goes high, the decrementing happens. In between, the gate is pulled low for one cycle, and when the gate goes high again, the decrementing happens from the first value, that is value number 4, and you decrement to 4, 3, 2, 1, 0. After the count has reached 0, the output falls for one cycle, creating a pulse.